Okay, so gentlemen, can you see the PowerPoint presentation up on the screen, that window?
Yes, with the really awesome rally looking car.
Yeah, that's a Toyota 86 or a BRZ. That looks like the Toyota model there. Um, and this one's advertising Motec injection. Um, Motec and Haltech are the two big names out there, and we have equipment from both of those guys. I've used Motec in racing for like data analysis, but I haven't done as much fuel injection programming stuff on Motec because honestly, the Haltech has a lot more like resources to help you through it. Motec's a little bit more secretive, but a lot of this EFI tuning stuff comes out of Australia. And those Australian guys, I mean, if you ever watch like the V8 supercars or anything, um, it's super popular. Cars are super popular down there. So that's where a lot of this good programming stuff.
Yeah, in Project Cars 2, they have the Toyota 86. They just don't have the Subaru BRZ.
Yeah, but if you know what, it's the same car. So if you're driving one, you're driving the other. They would both drive the same. So cool. All right, so I'm gonna maximize this thing. We'll get our drawing tools up on the screen, and we're gonna get going. All right, so a little bit of review from last week. 3 types of fuel injection systems, right? Throttle body fuel injection, port. So this would be example of TBI right here, right? Port fuel injection and direct injection. And direct injection is where we're spraying the fuel directly in the combustion chamber. All right, I'm killing myself because there's Jeremiah, admit. Welcome. Sorry for the waiting room. I didn't mean to set that up, and somehow I messed up that setting here. So anyways, welcome everybody. So we were just reviewing the EFI systems from last week. Throttle body fuel injection, port fuel injection, and direct injection is where the fuel injectors spray the fuel directly inside the engine. So a lot of your new cars use direct injection. And these are the cars that, can give you like 40 miles to the gallon, but it's not a hybrid. They usually have a feature direct injection. All right, so that was one of the things we talked about last week. Kind of continuing on that theme, we then talked about different types of tuners. We talked about how there is piggybacks. They kind of stink because you're very limited because you're modifying the stock ECU. We talked about performance proms in older computers and chip burners. Again, that was more of an older computer thing. And then that evolved into reflashing or reprogramming, which is what most folks will be doing if you're using the stock computer, right? So if you're going to run the stock ECU, but you want to modify the programming that's within it, then this is what people will do. Is they'll do the reflashers or the reprogrammers. And you could have fixed tunes that the company that made the programmer, like Super Chips, they might have some, hey, put in this tune for better performance or put in this one for better fuel economy. Or really good ones you can fully adjust, make all the settings adjustable, right? These are pretty popular too. Let's say you have a truck and you put big wheels and tires on that truck, and now the speedo's reading all screwy, right? It's way off. Well, that oftentimes can be fixed through programming to recalibrate that. So those are some of the things that those can do. But when you're using reflashers or
you forgot the lift kit.
Yeah, Yeah, well, assuming you put the lift kit on there too. It looks really silly if you lift the car and then it's got the stock wheels, but you know, the tire size, right? The tire size will change the revolutions per mile, and it'll throw off your speedometer reading. So you can oftentimes fix that through one of these reflashers. But with those reflashers, what's really important is that you make your program, you shut the car off, then you reflash or load that new program in there. So you can't do it while the car is running. The car's got to be shut off. You should have a clean type battery charger on there, or a good battery as you do it. It's certainly not a live type situation. And then lastly, we have our standalone ECUs, right? And these are where we put in a completely different computer, and we can program in there whatever the heck we want. There's no factory limitations. There's no OBD stuff that we have to worry about. So if we're really building a full, you know, off-road vehicle, like off-highway vehicle or race car, maybe it's a race buggy, maybe it's a truck, you know, if we're not worried about meeting OEM car standards, a standalone ECU would be the way to go. But keep in mind that a standalone ECU is going to cost typically a lot more money, okay? But what I like about the standalone ECUs is that, you know, most of these, you can actually make adjustments while the car is running on the dyno. So for tunability, they're fantastic. I mean, they're just awesome. And so we'll look at some videos of that today. Okay, so like I said last week, our focus is going to be on standalone stuff, but you know, a lot of all this still applies. So this Haltech Elite would be an example of a standalone ECU that you can program while the car is running. Where this Jet one, that actually this is the one that I have for my pickup truck, I can only modify certain things, and I got to do that when the car's off. Okay. All right. The big caution with doing programming is you can screw up a lot of stuff if you don't program it right. And what I'm going to try to do for you guys today is just to give you the ability to get in there and maybe load a base map and check that out. In fact, what I'm going to do on my screen is get this loaded up on the screen and mess around with it. And then if you are like, hey, I like that, that's cool, you can download this software and mess around with it on your own as well. It's pretty neat. In fact, you could even you could even write a tune for something, and then you know, in the fall, you know, we could try to load that in something if you were so inclined. So
no one makes something that will blow an engine up.
Right. Well, that's the thing. So and at the time, and you know, at the time they didn't have base maps for our vehicles, but we'll see today if there's some base maps, because the software has improved quite a bit. The guys are at Haltech and Motec, they're always updating their stuff. So all right.
Professor, I couldn't get the Haltech to download onto my PC, and I wasn't able to look at the videos, unfortunately.
Okay. All right. Well, you'll look at it today on my screen, and then maybe you can figure out how to get it working on your computer. I don't think that this stuff is compatible with Macs, though. I mean, just and not that I'm bashing MacBooks and stuff, because we have some. I mean, they're nice computers, but what you will find is in the automotive specific world, for like programming engines or looking at racing data, most of those software platforms are not compatible with Macs. That it's a PC based type thing. So All right, and let me just do a quick check of the chat and make sure that everybody's good. All right. Yeah, I'll tell you what. I'll be really honest with you guys too. It's hard to figure out like what day of the week is it, right? Like, so it's easy to get behind. My hope is if especially if after today's presentation you find this interesting, that you can go to Haltech's website, download the software, and just play around with it. And then but if you're more of a carburetor guy, that's fine. I just want you to be able to leave this class and know what the advantages, disadvantages of each type of pathway are. Okay. All right. So we'll clear those drawings and we'll keep moving. So this is all kind of stuff so far that we talked about last week. What we're going to talk about right now, which is a little bit more on the new side, is the basics, like the sensors and stuff. Right now, we are not going to be replacing the AT325 class, which is called engine. I think it's engine performance / I'm going to write CEC for computerized engine controls. I'm going to be teaching that class next semester, and so is Cheryl Toshima, and we're actually going to partner on some things on it. So I'm really excited about that. But that's the class where we really take a deep dive into all these sensors. Remember that when it comes to well, I was going to say when it comes to EFI, but you guys, because I know a lot of you are pretty computer savvy, just computers in general, the saying is, right, garbage in, hey, that's going to equal garbage out. So don't forget about that, because that will definitely affect you. So if any one of these sensors is you know, not working correctly, it screws up everything pretty darn good. Why is that class called engine performance? Well, because if one of these sensors, let's say the mass airflow sensor, it's producing a bad signal, the car's not going to have very good performance. And so if I can diagnose that I have a bad mass airflow sensor and fix it or replace it, now I'm going to restore my vehicle's performance. Okay. So sensors 101. I have these put in what is kind of their priority in the engine. So if you think about the, what does the computer or electronic control unit, ECU, what is it looking for? What's most important? You know, what sensor is priority number 1, and then what's the number 2, and what's the number 3? That's how I've listed these sensors in order to kind of give you some information about their hierarchy, like what's the most important. So the most important sensor out of all of them is going to be your crank and cam sensors. Okay. Now you might have a car where it's only got a crank sensor and it doesn't have a cam sensor, but a lot of vehicles have a cam sensor. Now, why would I need to have a cam sensor? Remember how we said that some fuel injection systems are sequentially fired, SFI, sequential fuel injection, meaning that they spray the fuel in the engine when that cylinder is going on its intake stroke? Well, if that's the case, I have to know when certain cylinders are on their respective strokes. So I need to know what the camshaft's doing. So if I have sequential injection, I need to have a camshaft sensor. If I don't, let's say I'm just throttle body injected, I don't need to have a camshaft sensor. I can get by with just a crankshaft sensor. And what further makes this kind of confusing is sometimes maybe they call it a crank sensor, it only has one sensor and it's just driven off the cam sensor. So here's what I'm going to write down on here is I'm going to replace this with RPM and TAC. I need some type of revolutions per minute, right? Some RPM or a tach signal going to the computer so it knows that, hey, the engine's turning, right? So the most important thing, if the computer doesn't know the engine's turning, why would it turn on the fuel injectors or fire the spark plugs? So that's why that's the most important sensor. The second most important sensor, the number 2 priority sensor, would be how much air is going into the engine. Air in engine, right? That would be the second most important sensor. Is I got to know how much air is going inside there. So there's 2 ways to do that. There's mass airflow sensors, like I have in the picture here, and they actually have some electronics on them. Usually inside there's a little hot wire, and then as air flows in, it goes through this. It goes from the air filter through this sensor. It flows over that wire and it gets a signal off of that. So you could say that the mass airflow sensor, it measures the airflow directly. The manifold absolute pressure sensor, or MAP sensor, this guy right here, he measures the airflow indirectly. And so what he's looking at as intake manifold pressure, and he knows as the intake manifold pressure increases, there's more air flowing into the engine. So let's look at how these sensors work a little bit better than I can just do in my drawings. We'll see how well this works here. Okay. Okay, so this one's on crank sensors here.
Of the crankshaft to control ignition timing and injection sequencing. The control unit can then trigger the ignition and injection to suit operating conditions. The position sensor may be mounted externally on the crankcase wall, or it may be inside the housing of the ignition distributor.
Okay, guys, I need some feedback from you. Can you guys hear that video okay?
I can hear it perfectly fine.
Okay, and remember,
Yeah, I can hear it.
due to bandwidth, that might be a little bit slow, but you're going to get most of it. And then one of the things I'm working on, and I haven't quite figured it out yet, these videos that I'm playing are copyrighted through CDX, and they didn't want me just to throw it on YouTube. I'd get in big trouble for that. But I'm trying to figure out a way that maybe embed them into our Canvas site. So if you wanted to watch them later, if you have the CDX book or online access, you do have, these are in there. I've basically got them from CDX. They do a pretty good job showing you stuff. So this first one's on the crank sensor, or what we'll call our tach signal that goes to the computer. And like the video was saying, that sensor could be located down on the crankshaft. It could be mounted in a distributor. It could be on the end of the camshaft, or it could have 2 sensors, one on the crankshaft and one on, driven off the camshaft together for sequential firing. Okay, so now that I know that you guys can hear it, I'll get it playing again, and it'll explain to us kind of a little bit more how the sensor works.
There are different kinds of crankshaft position sensors. Inductive type sensors sense the movement of the ring gear teeth on the flywheel, or a toothed disc on the crank pulley. These sensors do not make physical contact. The sensor is mounted on the crankcase wall. It consists of a stator with a central permanent magnet and a soft iron core surrounded by an induction winding. The housing around all of these components is insulated from them. The stator is positioned so that it has a very small clearance or air gap between the end of the soft iron core and the flywheel teeth. As the flywheel rotates, the teeth approach and leave the stator, and the air gap changes. As this occurs, the strength of the magnetic field changes. The winding is part of a complete circuit. So changing the magnetic field produces an alternating voltage and current. As the tooth approaches the stator, the strength of the magnetic field is increasing. This induces a voltage and a current flow in the winding. The polarity of the voltage is said to be positive, as it produces a current flow in the winding in a certain direction. When the tooth aligns with the stator, the magnetic field is at its strongest, but at that point, it is not changing. Voltage and current flow fall to zero. As the tooth moves away from the stator, the strength of the magnetic field changes again, and once again, voltage and current flow is induced in the winding. This time, current flow is in the opposite direction, and the polarity of the voltage is now said to be negative. Since polarity changes every time a tooth approaches and leaves the stator, the voltage produced is an AC voltage, and the current flow in the winding is an alternating current. Similarly with the toothed disc. As the tooth approaches the stator, the magnetic field is changing. It reaches a maximum when the tooth aligns with the stator, then changes again, decreasing as the tooth moves away. An alternating voltage is produced. It is the frequency of this alternating voltage that is used by the control unit to calculate engine RPM.
Okay. So in this example, they really went over the magnetic style crankshaft sensors. There's also Hall type sensors and optical sensors, but like I said, we're kind of hitting the highlights. I think what's important to note here is that it's got to be located pretty closely to this reluctor ring, and if it's too far away, it's not going to work. Also, this type of sensor, notice it's got 2 wires on it. That's how you can kind of pick apart those sensors. And remember, if this thing was not providing a signal to the computer, it would not know that the engine's turning, and the car would just shut off. So if I was driving down the road and for whatever reason this sensor failed, or it got knocked off of there by a rock because it was on my Jeep or something, the car would just shut off, right? That without that sensor, you're dead in the water. We will close that out. Okay, there we go. All right. Okay, so there's one other sensor we looked at, and I think I'll turn the volume down and we'll get that one going. And this one is on map sensors. So where the mass airflow sensor kind of made sense, air's flowing over it, it passes a little wire that absorbs the temperature, right? Like the wire gets colder as the air passes over it, and it's measuring the airflow directly. The map sensor doesn't make as much sense. So that's why I selected to play this video. All right, so this is the map sensor right here.
Sensor measures these pressure changes and converts them into an electrical signal. It's called a manifold absolute pressure, or MAP sensor. The signal may be an output voltage or a frequency. By monitoring output voltages, the control unit senses manifold pressure and uses this information to provide the basic fuel requirement. It can use a piezoelectric crystal. If there is a change in the pressure exerted on this crystal, it changes its resistance. This alters its output signal. The sensor is connected to the intake manifold by a small diameter flexible tube. The control unit sends a 5-volt reference signal to the sensor. As manifold pressure changes, so does the electrical resistance of the sensor, and this in turn produces change in the output voltage. During idling, manifold pressure is low, which produces a comparatively low MAP output. With wide open throttle, manifold pressure is closer to atmospheric, so output is higher.
All right. So let me turn the guy off. So this this map sensor is connected to the engine through a vacuum hose. And there is a, oops. So that's connected to the engine through a vacuum hose. And here, oops, gosh darn it. Try it one more time here. Here, I want to put up a term here. Speed density. So cars that utilize a map sensor, oftentimes I'll call it a speed density system, which kind of is confusing because it's not actually measuring the density of the air going in the engine. It's measuring the speed of the engine. It's measuring the pressure through this vacuum hose right here. It's measuring the pressure and it's calculating what it thinks the density is. So that's essentially how that system works, and how these get screwed up is, let's say you're working on the car and you accidentally disconnect that vacuum hose. All of a sudden, it doesn't know how much air is really going in the engine. In fact, it goes to maximum pressure. And to show you what I'm talking about, what I need to do is I'm just going to share my entire computer screen here for a minute. And then I'm going to put some stuff away and throw up the document camera, I think. Here we go. Let's see here. Yeah, there we go. There's my mouse in the way. Okay. So here, guys, I have here I got a vacuum gauge. And so you can see it goes from 0 inches of mercury all the way to about 30 inches. And then it does a little bit of fuel pump pressure. It goes to 10 PSI, so it's a vacuum pressure gauge. And if you look at it right now, if I can kind of maybe shim this thing to the side so you guys can see it a little bit better, you'll notice it's basically sitting at 0 inches of vacuum, right? We're at atmospheric pressure right now. So really, it's sitting at 0 PSI of pressure, but that's also 14.5 pounds absolute, right? Now, if I had a turbo or something and it was putting pressure in the manifold, you'd see it going that direction. And if it were running in the engine going down the road, normally, unless you're at wide open throttle, you'd have some vacuum going the other direction. In fact, if I can get my tools working right here. See if I can get this set up with my vacuum pump and give you some vacuum readings. Ooh, I'm losing the vacuum somehow. I got a leak somewhere in this system. So normally when the engine's running, it'll be running right about 18 to 20 inches of vacuum. Okay, that's pretty normal to run it, somewhere between 18 to maybe 22 inches of vacuum. When you open up the throttle, you let air into the engine, right? So when you let air in the engine, the vacuum goes away. So we can make calculations based upon the size of the engine. We can make calculations based on, okay, if I know the engine's, let's say it's a 2-liter engine and it has no vacuum, so I'm bringing in maximum amount of air, well, then we'll know how much air is coming into the engine. So we're kind of calculating the airflow based on how fast is the engine turning, what's the size of the engine, and what's the pressure inside the intake manifold. That's what a map sensor is looking at. All right, so let me put this back on the computer and I'll share the presentation to kind of clean that up. And
Changes in engine speed and look.
And what we saw here was that some of them vary voltage, some vary frequency, and it works off of a little piezo-resistive bridge in there, sensing those pressure changes. And it's connected by a vacuum hose. So it's one of those, like if you accidentally connect that vacuum hose, it's gonna go to maximum, it's gonna go to maximum pressure. And so the default is gonna be to go way rich. So if you disconnected this hose accidentally, it would just be dumping fuel and running really, really rich, almost like you had the choke on your carburetor. Why am I making such a big deal about these map sensors? Most of your aftermarket, fully programmable computers, Motex, Haltechs, that type of thing, they choose to use a map sensor versus a mass airflow sensor. In fact, if I back this up a couple slides and we look at the picture of the mass airflow sensor, the mass airflow sensor, one side is connected to the air box, right? The other side's gonna go to the engine. And that means the actual physical size of the mass airflow sensor is pretty tuned into the size of the engine. And so if guys are running a mass airflow sensor and they modify the engine or they put a supercharger on there, or they do, oftentimes they have to buy a larger mass airflow sensor or some type of other mass airflow that can handle the additional airflow. So why most of these aftermarket computers use a map sensor instead of a mass airflow sensor or MAF sensor is because the nature of it kind of limits you on what you're doing with the engine. Okay, so stock cars in their original configuration will utilize mass airflow sensors. Most of the complete, fully programmable computers and stuff, they use map sensors. All right, let me clear all that stuff out. Switch it back to this. Oops. And we'll go to our next group of sensors. So next on the list is kind of a toss-up as far as their priority. So I put them on the same page. We have our temperature sensors, and then we have our throttle position sensors. And then cars that are throttle by wire, meaning that there's no throttle cable between the accelerator pedal in the car and the throttle, that means that that's all controlled electronically. So they will all also utilize some type of accelerator pedal position sensor. If you remember a few years ago, Toyota was having a pretty big debacle with what they called unintentional acceleration, where they had some sensors that were failing, some programming issues, floor mat issues, and cars were accelerating and running people over on their own is what the complaint was. Those were cars that had accelerator pedal position sensors. And most all new cars will have an accelerator pedal position sensor. But going back to the 1980s, cars that were fuel injected would have a throttle position sensor. So the computer knew what position the actual throttle was in. It's another way to fine tune how much air is going into the engine. Likewise, since the earliest days of fuel injection, and the oldest car I ever worked on that had fuel injection, 1968, Volkswagen Squareback, had EFI on it, and they called it D-Jetronic. Anyways, even that thing had a temperature sensor. Temperature sensors are also known as thermistors. They change their temperature with, they change their resistance with temperature. Most of these, I can't remember on that 1968 Volkswagen, but most modern stuff from the 1980s moving forward, they're a negative temperature coefficient thermistor, which means that their resistance lowers with temperature. And what we're going to do is we're going to look at how these things work.
This sensor gathers information on throttle positions to allow the control unit to make adjustments according to operating conditions. It is located on the throttle body and operated by rotation of the throttle spindle or shaft. Throttle position is sensed by a contact type switch or a potentiometer. The switch type has two contacts, idle and full load. It can be supplied with a voltage to the center terminal of its connector. At idling speeds, the full load contacts are open. The idle contacts are closed, and they signal to the computer, which provides for a mixture to maintain idle quality and stability. Slightly rotating the throttle shaft opens the idle contacts. As the throttle approaches the wide open positions, the full load contacts close. The ECU reads the full load signal and enriches the mixture to suit. The idle contacts closed signal can also be used with the engine RPM signal to the control unit to stop fuel delivery on engine overrun. This can be done, for example.
Sorry, guys. I just wanted to turn the guy down. Okay, so this first one in the first half of this video has the same acronym, but this is the older style. So if you work on a car that's from the 80s, it might have this first style. And this is a throttle position switch. So it's a TPS, but you can see that it's not a sensor, it's got switch contacts in there. So then let me fast forward this video to the actual sensor. And so in the, as we went from the 80s to 90s and actually even early on, like domestic manufacturers like GM always used a sensor, but a lot of your imports used a throttle position switch. But as time moved on, everybody went over to sensors because it gave them more information. So here we have this guy right here is the sensor. And so the throttle position sensors are going to be 3 wires. They're typically going to receive a 5-volt reference. They're going to have a signal wire coming out of the middle, and then they're going to have a ground on the other end. And they have a little wiper arm that moves back and forth over this resistive surface, so it can sense not only what position the throttle's in, but it can also see how quickly the throttle moves. So here we're seeing the voltage change as we're sweeping open the throttle. So I kind of relate these sensors to like your accelerator pump in your carburetor, in that if your throttle position sensor is not working correctly, oftentimes the car will develop a hesitation on acceleration. You'll go to punch it and the car will go, and it'll hesitate and then it will accelerate. All right, let me check out the, all right, everything's okay on the chat. Remember, if you have a question, you can really just blurt it out. But if you want to do the hand raise thing, or just let me know that you have a question in the chat, I'll check it for you. So most of your throttle position sensors they change their voltage, and so as you open up the throttle, the voltage goes higher and higher. So there you go. If you disconnect them, some cars will default to high voltage and the car will run really rich. Other cars will default to no voltage and the car will have a severe hesitation. Kind of depends by car to car on how the car is programmed and set up. But that lets the computer know, hey, what position is the throttle in? Now this same sensor here, with its varying voltage, there is a more like electronics name for it. Does anybody know what these 3-wire sensors, what they call them in like normal electronics industries and stuff? Well, you guys will like this one. A lot of times they'll use the acronym POT for potentiometer. Okay, so this is a 3-wire potentiometer. This same sensor would be used on the accelerator pedal for an accelerator pedal position sensor. So it knew how hard you were stepping on the accelerator pedal, and then a little motor could open up the throttle for you. All right, switch back.
So
Go ahead.
my mom's boyfriend, he had a Chevy. He had like a new Chevy,
Mm-hmm.
and so he drives for Lyft.
Okay.
He does driving for Lyft, and he was on the freeway, and he went full wide open throttle, but instead of it going, it stalled, and then it just took off. The engine stalled and it took off, and then he came back and we did an OBD2 test, and it came out to like a throttle sensor was going out, like a throttle sensor code.
Yeah, yeah, so that's pretty common. If I go back to this part, you can see that this particular style, it's very mechanical on how the sensor works, right? And you actually have an electrical contact rubbing against another electrical contact, right?
Yeah, it
So
was
what
it was
happens,
weird because then I actually
it'll
was
be a flat spot.
driving with him too, and it was weird.
Yeah, yeah, so if you think about it, you're usually working this throttle at like, quarter throttle in this range right here. So over time, it will develop like a bad connection, a flat spot we call it, usually in that area that you're all in it all the time. And then you'll go to accelerate and it'll just go, ugh, and it won't go because the computer didn't know that you quickly opened the throttle. And then it has to play catch up and look at other sensors like, oh, the engine's, well, it's looking at the mass airflow or map sensor and engine speed, and it has to kind of gather, figure it out. And it takes a certain amount of time for that to happen. And that's how you get that hesitation, right?
Yeah, but the weird thing was it was like a brand new car too, so it was brand new.
That's interesting. So did he take it in? Did it ever do it again? Did he take it
Yeah,
in?
he was like, well, if it does it again, then I'm going to take it in, because it didn't do it for a while, and then it did it again. He was like, yeah, I'm just going to take it in and just trade it out for something else.
Oh, I was going to say, do you know what they found on it at all?
I don't know what they found on it. I just know he took it in,
So,
and then he got a Nissan Rogue.
okay. So being that it's a new car, I mean, you could still have a component error. Oftentimes on new cars, though, what they find is there might have been a flaw in the programming, and we'll call cars back in and have them reflashed at the factory to cure certain drivability problems. So it could have been just a programming issue that at a certain temperature, a certain speed, rate of acceleration, that the computer would basically get logic locked for a second and then freak out and cause that hesitation.
Yeah.
So it's not outside of the box on today's cars to have a failure that's not hard part related, but it's not component related, it's software related. So that's another possibility. But if you had an older car that had some miles on it, I definitely would be very suspect of the throttle position sensor based on the complaint that you described. So
Yeah, but it was weird.
yeah. So we talked about the throttle position sensors. I don't know, did we get, let me see if I can move this banner here. Oh, we didn't did we watch the video clip on coolant temp? Let's check that out real quick.
Thermistors are semiconductor resistors. Their electrical resistance varies according to temperature. This makes them suitable for temperature measurement and for electronic control operations. There are two main types of thermistor: NTC, or negative temperature coefficient resistors, and PTC, or positive temperature coefficient resistors. NTC resistors have lower resistance at high temperatures, which means they conduct current more readily when they are hot than when they are cold. NTC resistors are commonly used in temperature sensors in engine management systems.
Okay, so that was a quick one. So just to hit some highlights, these temperature sensors, they'll be located in the intake system, measuring the temperature of the air that's going into the engine. They'll also be located screwed into a coolant passage, like you saw right here. It's usually close to the thermostat area. Now, if I go back to what it looks like over here, you can see that it screws into the water jackets or coolant passages. And let's see, here's the engine and it's screwed in there. It only works if this sensor tip is actually touching the coolant, right? So what throws it off sometimes is if the car gets really low on coolant and there's no coolant touching this, the car could be overheating and the computer doesn't even know it because there's nothing there to transfer the temperature to this thermistor. So keep in mind, all these temperature sensors, they assume that there's coolant in there. They don't necessarily know if there's no coolant passing over the sensor. Like the video clip showed, these are typically negative temperature coefficients, which means that they have high resistance when they're cold and their resistance drops as they get hotter and hotter. And they're not linear. They kind of have this slope to them. How I like to test these is if I disconnect the connector, it should go to max voltage and it'll make the car run real rich. And when I jumper wire this thing, it should go to maximum hot. So they're pretty straightforward. They do fail occasionally. They're relatively important because if you disconnected this temperature sensor, the car would stay in open loop. It would run really rich, that type of thing. So, and on a modern car, this same sensor might be used to control like the electric fans and other features. These types of sensors are also used in things like your automatic transmission, so the computer knows what the fluid temperature is. Pretty common sensor, right? So that type of sensor is called a thermistor. All right, so now we've covered all the major sensors to basically make the engine run, right? RPM, throttle position, airflow, temperature, those are the biggies. But your feedback comes from either an oxygen sensor or an air-fuel ratio sensor. And there is definitely differences between the two. Oxygen sensors, the one thing I want to stress on these guys is that they are a narrow range of sensor, meaning that they can really only detect the air-fuel ratio between about, let's say a little bit over, 14 to maybe, 15.5 to 1, 15.5 here. They can't detect what the air-fuel ratio is over a wider range than that. Most of them make a 0 to 1 volt signal, but again, narrow range used on the factory for a lot of cars. Now, air-fuel ratio sensors, or AF sensors, they're considered a wideband sensor. They work quite a bit differently. They produce a different type of signal, but they'll be able to measure the air-fuel ratio anywhere from maybe an 8 to 1 air-fuel ratio all the way past an 18 to 1 air-fuel ratio. So they have a much wider range on them, and that's why they'll be called a wideband sensor. Oftentimes they'll have more wires going to them. They run twice as hot as a regular oxygen sensor. Definitely costs a little bit more, but you can get more information from them. Why wideband sensors are important to us is from a performance standpoint, we'll commonly be running air-fuel ratios that are maybe 12, maybe 12 and a half to 1, and a narrow band oxygen sensor can't read down that low. It's just going to say, hey, this thing's rich. It's not going to know the difference between a 13 to 1 air-fuel ratio and a 12 to 1 air-fuel ratio, or a 10 to 1 air-fuel ratio. So these sensors are important because they give the computer a feedback, a report card, if you will, to say, okay, this is what you did, and this is how well you did it, right? And do you need to adjust how much fuel you inject in the engine the next time based on this sensor? because of that, if this sensor is reading incorrectly, it can really throw off the readings. If the oxygen sensor isn't working, usually it's going to default to running rich. And these oxygen sensors and air fuel ratio sensors, for that matter, they do have a lifespan. So I'm going to put down, it's kind of like a battery. Notice how I said it produces a voltage signal right here. So think of it, if it's producing a voltage signal like a battery, it's got a lifespan of a battery, right? The battery in your car only lasts so long. The same thing with these sensors. You know, if you got 80, 90,000 miles out of an oxygen sensor, you're doing pretty darn good. In fact, a lot of the older ones, they were really only made to run like 30 or 40,000 miles. So with that being said, we'll clear the drawings. We're going to check out how it works.
The oxygen sensor, also called a lambda sensor, is mounted in the exhaust manifold or the engine pipe. Its sensing portion is exposed to the stream of exhaust gas. It detects leftover oxygen in the exhaust gas and sends data to the control unit. The control unit uses it to fine-tune the pulse it sends to the fuel injectors. The sensor consists of a tube closed at one end and made of zirconia ceramic or titanium ceramic. Its inner and outer surfaces are coated with platinum. The outer closed end is covered by a louvered metal shroud that protects it from breakage but still lets the exhaust gas contact the tube. Its inner surface is in contact with the air. A wire contacts the inner surface of the tube through a spring and an electrode bush. This provides the electrical link to the control unit. The inner and outer surfaces of the ceramic tube are coated with porous platinum. The side facing the exhaust gas has a highly porous ceramic layer on top of the platinum, which lets oxygen through. The ceramic tube with its platinum electrodes is now a porous, solid electrolyte. At temperatures around 350 degrees Celsius or 662 degrees Fahrenheit, it becomes a conductor. One side detects the level of oxygen in the exhaust gas. The other detects its level in ordinary air. If the levels are different, a voltage is generated between the two sides. The control unit compares this voltage to a preset level. Below the level indicates a lean mixture. Above it means a rich mixture. The control unit may then adjust the pulse to the injectors to maintain correct mixture. This fine-tuning is needed for the catalytic converter to function properly. Some sensors have built-in heating elements powered by the vehicle's electrical system. It helps them reach operating temperatures more quickly.
Okay, so yeah, most modern cars, they're going to have a heater circuit in there. And so any oxygen sensor, well, I shouldn't say any, but most oxygen sensors you see that would be 3 wires or more, will have a heater on the inside. Now, speaking of the heater, how hot did we say these suckers were going to get? Well, a regular O2 sensor runs somewhere around 600 degrees on the Fahrenheit scale. An air-fuel ratio sensor, those things, they'll run double that, 1200 degree Fahrenheit. In fact, I think the failures of air-fuel ratio sensors, they seem to fail a little bit more often than regular oxygen sensors, and I think a lot of it has to do with how hot these things run. Speaking of the heat, I would recommend, if you're putting in one of these sensors, make sure that it has some of that gold-colored anti-seize or silver-colored anti-seize on the threads. Not so much that it gets in the sensor here, but that it's on the threads, because these things will want to weld themselves in the intake, in the exhaust manifolds. In fact, a lot of cars, like, you know, let's say you're working on a Toyota RAV4, I mean, just don't even try taking it out of there, because it's going to strip out the threads. Just replace the whole manifold when you go to change the sensor out, because they were almost always just welded in place, because they run that hot. The other thing, I don't know if you guys caught it, But these sensors, if I rewind this to this picture right here, essentially what they're doing, how they work, if I make it real simple, is they are comparing the amount of oxygen, or O2, on the outside here. They're comparing it on the outside of on the outside air, which actually goes through a little vent. There's going to be vents in this little cover or around the wire, but that's going to put fresh oxygen from the outside on the inside of the sensor versus the exhaust gases going through here. And there might be a little bit of exhaust gas in here. So it's comparing basically what's the exhaust that's inside the exhaust system to the amount of oxygen outside the exhaust system. We know when the engine runs really rich, there's not very much oxygen, if none at all, inside the exhaust system, because we're burning it all, right? So then there will be a big difference between the two. It'll make a voltage. So remember, these are like a battery. They have a lifespan. It's not an uncommon failure item. And if usually when they fail, they'll fail to thinking that, hey, it's rich all the time. Or I'm sorry, usually when these will fail, they just won't produce a voltage signal, and they'll say, hey, I'm lean all the time, and then that will make the car run rich. So I want to make sure I say that right. Because this sensor is producing a voltage signal, right? Maybe it's an oxygen sensor and it's producing 1 volt when it's supposed to be rich. So that means the engine runs rich, it produces a 1 volt signal. Well, if this thing's dead and it can no longer produce a 1 volt signal, what it's going to tell the computer is it's going to tell the computer, hey, I'm not producing a signal. I must be running lean. And what's the computer going to say to that? Well, the computer's going to say, okay, dude, well then you need to add more fuel. You need to make the mixture richer. Not right, but rich. Anyways, so again, this sensor, if it fails, it'll tend to make the engine run really rich again. All right. So that's our oxygen sensors, our air fuel ratios. Sensors are almost kind of like an O2 sensor within an O2 sensor. But heck, it'd take me 2 hours to talk about how those work. So you kind of get the basis idea though. Same things hold true, and when the sensors fail, oftentimes the engine ends up running way too rich. Okay, outputs, right? All those inputs are there to make sure that the computer then has the right information, it can make the right decisions, and then control its outputs correctly. So what are our major outputs? Well, they're things that some of these we've already looked at, like the fuel injectors, right? How much time do I turn on the fuel injectors, right? But it could also be things like, see this thing right here, this is an idle speed, an IAC valve or idle speed controller. It's basically an air bypass. So this little gasket goes to it and it lets air go around the throttle body to control the idle speed. This thing right here, this is a variable valve timing control solenoid. It controls oil flow through the engine to move the camshaft around to control the valve timing. So there's various outputs that the computer then has to control. And then on newer cars, it even has a little motor that actually opens up the throttle. So you step on the accelerator pedal position sensor, it says, hey, Jonathan's stepped on the accelerator pedal position sensor, he wants to go ahead and open up the throttle. And then it looks at the throttle position sensor to see if it actually did, in turn open up the throttle. All right. So what we're going to do is look at some of these outputs.
In the electrical system, detecting elements sense engine operating conditions and relay this information in the form of electrical signals to the electronic control unit, or ECU. The ECU is a small computer, programmed with the operating characteristics of each individual application. This information is stored in its memory. The control unit processes input signals to determine the amount of fuel required by the engine at that instant. It then grounds the injection valve circuit to open the solenoid-operated injection valves. The length of time injectors stay open in milliseconds determines how much fuel is injected. A basic EFI system needs input signals on ignition switch operation, engine cranking, the amount of air entering the engine coolant temperature, throttle position and engine speed, and battery voltage. The varying data received from all these inputs allows the ECU to arrive at its injection setting. This vehicle began from a cold start and has been running only a short time. It is now operating in top gear with a light throttle only. What influences its fuel requirements? A relatively small volume of air is entering the engine. The throttle piston is associated with economy or cruising conditions. Engine speed is in the low to mid-range. Coolant temperature is still below normal. These factors combined produce a fuel setting. It is less than if the throttle were opened suddenly for acceleration or to overcome increased load. However, it is more than it would be if coolant temperature were at its normal level. The varying signals can be supplied by variable resistors, by switch contacts, by voltage pulses from the ignition system, or by sensors.
Okay, so if we kind of summarize this, your two major outputs of the computer are what to do with the fuel injectors and what to do with when to fire the spark plugs, what to do with the ignition system, right? Those are the two main outputs, fuel and ignition. And I did want to take a kind of a side note because this particular example showed us a weird style of air measurement device on the intake that I actually didn't talk about, but it's not too far off the mark. This style, this thing here, he is called an AFM or airflow meter. And very mechanical in the way it works. In fact, my Miata has one of these on there. As air goes into the engine, as air flows into the engine, it pushes that little door and moves it around. You know what's connected to this little door? A potentiometer, just like you had on your throttle position sensor. So a wiper arm here moves back and forth on the potentiometer, and that in turn then sends a signal out of this thing to the computer to let it know how much air is flowing into the engine. Pretty mechanical in how it works. But it would tell it how much air is going in the engine. The computer can then figure out what to do with the fuel injectors. And also another important output is when to fire the spark plugs. So related to that, we got one more video clip. For this one, I'm going to fast forward a little bit. So we're going over the crank sensors and different things. Here's what I want to get to right here.
Load operation, the emphasis is on economy and drivability. At full load, it is set for maximum torque without detonation. Using the digitally stored map, the ignition point is set for each operating condition without affecting the settings for any other condition. All of this raises an engine's overall efficiency for all operating conditions. Corrections to ignition timing, combined with those to the injector opening time, provide the optimum values to achieve the best combustion. With higher compression ratios, there is more risk of detonation and damage to the combustion chamber. A knock sensor allows ignition timing to be calibrated to achieve the best setting for normal operating conditions. Knock or detonation can then be eliminated separately using closed-loop knock control. When a detonation signal is received, the control unit retards the ignition setting to bring detonation under control. A turbocharged engine is different. Simply retarding the ignition could increase the already high temperatures at the exhaust-driven turbine. But reducing the boost pressure at the same time brings detonation under control quickly. As soon as knocking is detected, ignition is retarded, which works immediately. Reducing boost takes longer, but as soon as it takes effect, the control unit returns ignition timing to its optimum value.
Okay, so we also snuck in another sensor on you, right? And we got into some turbo stuff. So here's a turbo, it's making boost pressure. But the sensor we snuck in on you was this guy right here. This is called a NOx sensor. And it's almost like the oxygen sensor for your ignition system because it can tell you when the engine is pinging or knocking. And so that's kind of like feedback for your ignition system. Nice little shot of a GTR right there, right? All right. The other thing I wanted to show you, yeah, the other thing I wanted to show you was this. This is called a map, right? And this is the map for the ignition profile for whatever car. This is the table that's programmed into the computer. Now we typically look at these in a two-dimensional mode because it's easier for us to understand it in a two-dimensional mode. But if you lay over all three axes, you know, you end up with this type of graphical deal. These are what we as tuners would have to program into the computer. All right. So with that, now that we've got all the sensors and stuff out of the way, right? If we were going to set up our computer, well, the first thing we'd have to do is we'd have to wire it in. If it was an aftermarket computer, we'd have to wire that sucker in to get it to work correctly. And I do have a video clip on here of how to do that, but we're running a little bit long on things. I'll show you where this clip's at on Canvas, because I do have a link to this. There's different ways to do it. You could get a plug and play computer directly plugs in, or you could use a wiring harness that you buy from the supplier like this and wire that in. But that is one of the major stumbling blocks with electronic fuel injection is how do you wire it in, right? Okay, related to that, like I said, you can get some that just plug right in there. And so we actually have a video clip of Haltech putting what they call a Pro plug-in, which is exactly what we have in our Infinity G35, where it used the factory wiring and it plugged right in. Once you get that computer wired up in there, though, now it's your job to tune it, right? So for that, we will watch some of this video clip right here on Haltech dyno tuning. Here we go.
Are you open?
Uh-oh. Hang on 1 second. I'm going to switch the screen here, new share. I'm going to go to Dyno Tuning Basics. I don't know how they got my girlfriend on the screen, but they do. All right. All right.
Yeah, lucky bastard.
Yeah, yeah. Now, so here are the guys at Haltech. Remember, they're down from Australia. And you know they're cool because they're picking up rotors, right? And in this little video clip, they go over how their dyno works and everything. And I'm going to skip by a lot of that stuff. It's very similar to ours, except you'll notice it doesn't just have the one big, huge roller. Their dyno has the two smaller rollers. And in order for it to work and apply enough load, they actually have a electric brake, an eddy brake right there that he's got his hands on to apply additional load to the engine, okay? Because the rollers itself don't weigh as much as ours does. Then it's got a load sensor there so it can measure how much torque is being applied to the drive wheels. All right, so we get all that out of the way. And he gets it strapped down. He gets his car hooked up on there and stuff. And now we're going to watch how he does the dyno tuning. So with that, I'll turn the volume up and we'll get this thing going.
Even out on the road, he's still buckled.
Yeah, that's funny that he's buckled. I didn't, yeah.
As I apply more and more throttle, so I'm pressing the throttle pedal in the car down now, 16, 18, 20. We can see that our torque at the rear wheels is going up and our power in kilowatts, bottom left-hand corner, is also going up. But our RPM in the car is remaining the same. So if I go more and more and more throttle, same road speed. So essentially I'm driving up a hill, but I'm stuck at 60 kilometers an hour. I can't go any better. Okay, so right now we're at 2000 RPM and we're at 0 manifold pressure. We're not in vacuum and we're not in boost pressure. Our air fuel ratio is around 13.8 to 1. Our throttle position to hold here at 55 kilowatts at the wheels is 28%. Now, if I press my foot down a little bit more, we now have a boost pressure of 4 psi, but the same engine RPM. We've moved into a different load cell, meaning that now I can tune this site here and tune my fuel, my ignition timing, and my boost pressure at this site. If I come off the throttle and reduce the throttle position, same engine RPM, but now I'm in vacuum. So now I can come across and tune this load site. So essentially, I would want to go through and tune all of my load sites at 2000 RPM, or as many as I can get to. Then, once I've done that, I'm going to let more speed out on the dyno. So I'm going to increase the dyno speed. My RPM will go up because I'm allowing more roller speed. My next load site, 2,250 RPM. There we go. I'm now at 2,250 RPM. I'm at the next load site up. I can go through and I can see my mixtures. I can see my ignition timing. I can see what my short-term O2 corrections are doing. More throttle position, up, 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 up. Less throttle position, down, down, down. More and less. If I let out more RPM, I can put the trace on here in the Haltech software. So I'm just going to let more and more, and I'll let the dyno come up to now 125 kilometers an hour. And now I'm up at nearly 3,500 RPM. I'm going to leave the same throttle position, but I'm going to bring the dyno speed down and down and down. So let me bring the, oh, you can hear it dragging us down. Same throttle position, or I'm trying. Up and up and up. So now I'm stuck or locked at 2250 again.
Okay, let me pause it right there. If you notice, there's this, if I turn on my drawing tool, there is this little box thing over here, and you can see where he's highlighted it here. And if he drives the car in the right speed and gets it right in the right load value, this little box turns green because he's driving the car right where he's selected. And that means he's ready to tune that cell. So he basically screws around with the load from the dyno and how much he's pushing on the throttle of the car and how fast the car's going, so he can get into each cell, and then he can type on the keyboard and either increase the amount of injector on time or decrease it. So remember how I said that we usually look at these in two-dimensional tables? Here's the table for his base fuel, and he's driving it at different speeds, different loads on the dyno, and trying to get the right amount of fuel for all those cells. So he's either adding fuel or taking it away, and then he's looking at what is his air fuel ratio over here while he does that, okay? So again, what I will do is I'll show you where I have this link on your Canvas page so you can watch the whole thing again. It's one of these things, you might have to watch this video 3 or 4 times before you really starts to sink in. But it's pretty cool, and this is why I've told you guys that it's really hard to tune on the road, because it's hard to hold an exact speed or load on the road, and so having the dyno is much more of an advantage to do some of that stuff. So, all right, I'm going to move this back to our presentation, and we will keep stuff. We will keep stuff going. So I do have some questions here. Like I want you guys to keep thinking about what's better, an EFI or a carburetor, and then what do you think more makes more power as you're tuning stuff, right? As you're adjusting stuff, tuning the fuel or tuning the spark, right? I want you to think about some of those, and we'll probably finish today's lesson, and we'll be looking at this video. But before that, what I want to do now is actually open up the Haltech software and play around a little bit with it. So I'm just going to move this to my whole computer screen, and I'm going to...
After we've steady state tuned as...
I'm going to minimize some of this stuff here, because we got 25 things up and they're in the way of what I'm trying to do. All right. So can you guys see my desktop now?
Yes.
Beautiful, thank you.
Yes.
I've loaded the Haltech software, and I'm clicking the icon that says Haltech ESP. And it's got a thing that comes up that looks like that. All right, no, I don't want that. I'm gonna shut off the document camera, so that's not in the way screwing things up. All right, so this is the Haltech software. I'm gonna close out the annotation tool, get that out of my way. And you can get this software for free from Haltech's website. And they've made a bunch of updates to this thing. They got their YouTube video link and Facebook and how to order stuff and all kinds of stuff. And firmware update would be updating the firmware inside your Haltech computer. But what we're going to do is we're going to try to make a new program. And the easiest way to do that, like let's say I had my car. Now, my car is, let's say, well, we're going to take my wife's 1991 Mazda Miata, and I wired in this Haltech, and I want it to run my Miata. Well, the easiest way to do that would be to load a base map. So I would go to New, and I would tell it, well, what computer do I have? We actually have a really nice Haltech 2500 ECU, so that's what I'm going to select. So it's loading that Haltech ECU. It's loading kind of like that firmware to run that computer. So it's doing that now. Then I want to load the base map, because that will make it, that'll be a lot easier than starting with nothing. If they don't have a base map for me, then I have to figure out all that stuff myself. And so what I'm going to do is I'm going to go open, and you can see all these different makes and models. I'm going to click Mazda MX-5, right? Because that's a Miata. Our car is not turbocharged, and it's not old enough to have variable valve timing. So it's this one. I'm going to select that, and it's loading up for me a base map. So you'll notice down here in the corner, it says the ECU is disconnected. You know, if you hooked up the computer through the USB cable, that would change the ECU connected, and you can make live changes on the computer. So here I'm looking at my base ignition timing. Let me switch this over to base fuel. Okay, so can you guys see this fuel table up on the screen right now?
Yes.
Okay. So let me explain to you what we're looking at, because it's a little weird. It does say fuel load. I did convert this already to PSI. Okay, normally, remember Haltech, these guys are from Australia. So everything's going to be in metric by default, right? It's going to be in kilopascals and stuff like that. But you can go in there and switch it. It'll be in kilometers per hour instead of miles per hour. I already went in and made some of those adjustments on here. So it's measuring, here's my fuel load, and it's measuring pressure on this top bar in PSI or inches of mercury, just like on the pressure gauge that I had earlier, right? Just like on this gauge, it's measuring what we had. So I wanted it to look the same way. So because this thing's not turbo, the highest it goes to is 0 inches of vacuum, right? If it was a turbocharged model, then you would see pressure coming up over here. And then we got our RPM, right? 500, 1,000, all the way up to 8,000 RPM. And then so as we would drive it on the dyno, or I guess down the road as we were feeling adventurous, if we got to, let's say, 3,000 RPM at 20 inches of vacuum, we'd be running in that cell right there, and this green dot would be up there. And then if we typed in the keyboard, we could adjust this thing. So let me erase that. Let me turn it back on my mouse. And what you can see is I can select different things. So let's say this is right where we were running, 20 inches of vacuum at 3,000 RPM, just lightly cruising. And right now it's a 60.2. Well, maybe I want that to be 62.2, right? I could then change that cell, and then burp, the car would hiccup for a quick second, and all of a sudden it's injecting more fuel. Now, what do these numbers represent? How much fuel the engine's going to get, but that's not really what they are. What do you guys think these numbers are really relating to? Because it's not 62 milliseconds of fuel injector on time, that's for sure. What do you guys think? Well, it is kind of a trick question, but it is something that we have talked about in our class all semester.
Volume?
Volumetric.
Wouldn't it be volumetric pressure?
It relates to volumetric efficiency. Do you remember how I said for volumetric efficiency, most engines at best are maybe 85% efficient at wide open throttle, right? You know, and then if I had a car that was a turbocharged car, maybe it would get to 100, maybe 110% volumetric efficiency, because we're getting more pressure forcing the air into the engine. So basically, these numbers represent volumetric efficiency, and we know the volumetric efficiency is going to correspond to how much air is entering the engine, right? So if we go, okay, well, how much air is entering the engine? Inject this amount of fuel, like that. That's really the number that you're doing. So you'll notice the base map that these guys at Haltech programmed. If I switch this back over, this base map, these guys have determined, hey, at wide open throttle, so 0 PSI, I'm going to be at wide open throttle, and somewhere around 5,000 RPM is where the car is the most efficient, makes peak torque, and at that level, they tested and they figure you got 86.8% efficiency. So that's what they dialed in there, and that's where it's going to be given the most amount of fuel, right? If I was looking at my air fuel ratio sensor and it said the engine was running too lean right there, I would dial in something else. I'd say, okay, I'm going to go to 90, and then it would be commanding more fuel. So basically, what you're doing as a tuner on the fuel base map is you're setting up the window of how much fuel the engine's going to get by telling the computer the volumetric efficiency of the engine, and then it determines how much fuel to give it. And you're trying to get it as close as you can possibly to the air-fuel ratio you want, so that it has to do the minimal amount of correction with the oxygen sensor, okay? You want it to be like you could throw the oxygen sensor away and it'd still be running pretty damn good, right? Maybe just slightly on the rich side of things is what you're trying to do on this table. Now, if I get rid of all my scribbles here and I went to another table, right? What's my other major output? Ignition timing. So on this table is where I get to program in how many degrees of spark advance before top dead center do I fire the spark plugs. And again, you can see at lower speeds and load values, I can you know, have quite a bit of advance, and then I'm taking it away. What I will say, because I'm looking at this graph and I'm like, ooh, I don't know about that. Like they have, if I turn my drawing tool back on, they have a ton of advance at very high RPM. Well, I guess there's no load here, right? But if I go to, let's say I'm at relatively low RPM, let's say I'm at 1500, but I'm at wide open throttle, I don't have a lot of advance right there, right? So I'm looking at this graph and I'm looking at, you know, there's definitely some stuff that could be changed on here, but the basic concept is that when you're cruising down the road, you have light load, so I'm in the green, and I'm at a lower RPM level, I can usually get away with more spark advance. So you can see I got 38, 39, 40 degrees right in here. But when I go to wide open throttle, I'm at high load, I better take that advance away, especially at lower RPM levels. And then at higher RPM, I can add a little bit of that advance back in. So this is
although if you're still at like 1500 RPM at like wide open throttle, I would think something else would be wrong though.
Well, remember, it's the engine as it accelerates is going to accelerate through that point, right? So if you stab it and you go to wide open throttle and it started at 1000 and it does quickly rise through there, but for a split second, it might be at 1500 RPM at wide open throttle. So that's why that little spot is on the chart on there. Every spot that the engine is going to operate in, you have to set up your tune, and then for the in-betweens, right? Because we go from 1500 RPM to 2000. That's where the software will kind of average out in between those two. So, anyways, you know, high load, low speed, I can't have nearly as much spark advance as I can at light load. You know, even light load, high speed. So anyways, this is where you set up your base timing. Well, we talked about a knock sensor and stuff. And if I switch this back to my mouse, you can see that there's a separate table where you would program in what's going to happen when it detects ping and knock, and how much does it retard the ignition timing on there. You can program in what you want your rev limiter to be, right? So you can set that, and notice this one. What are you looking at? Well, here's your coolant temperature and here's your rev limiter. So we've set the rev limiter to be lower when the engine is really cold, and they set the engine, and then when the engine's warmed up, it's got a 7,500 RPM rev limiter. When the engine's like overheating, when it's running really hot, they lowered it back down, right? So, like I said, the advantage of a aftermarket fuel injection system is that you can control all this stuff. You can type in here whatever you want. The nice thing about having a base map is you have something to start with, right? and that saves you a lot of time. But I'm gonna type up here that when I think of a base map, and all these things that we've looked at here, right? The fuel, the ignition, and I should have drawings. Let's get that text tool up here. When I think of this base map, I want you to think of this as like a base coat of paint on your car or on your house, right? And so it, it gets some color on there. It sets up that protection, but it's not your final coat. It's not your final tune. So a base map is there to get the car running and the error kind of on the safe side, but it's definitely not going to make the most amount of power and be perfect for your configuration necessarily. Okay. So although you could run the car off the base map, you're not going to see its full potential if you're just stuck driving around on the base map. Let's say you have a car that maybe there's no base map for it. So what I'm going to do now is I'm going to switch it back to the computer. I'm going to clear my drawings. Let's open up a different one real quick. And Haltech, ECU maps. And we have a Toyota Celica, and guess what? They don't have a base map for a Celica, right? They have a Supra. I don't know what a Soarer is. They got a Land Cruiser. Of course, remember, this is Australia, so they have some different models. And if I did some research, maybe the Chaser is like our Celica. I don't know. But let's say, they don't have that Celica. I'm going to select JZ. Let's see what this guy is. These are all one JZ, and then the Supra is a 2J. That's a 6-cylinder. All right. So no, I don't have a base map for that car, right? So here's what I'm gonna do. I'm gonna say new. I'll tell it what computer I have. Maybe I got the Elite 1500 this time. The different computers give you more options, like an Elite 2500 can control 8 fuel injectors, and I think an Elite 1500 maybe it can only do 4. Or anyways, there's different options. How many things can the computers control? That type of thing. So it's going to load all this stuff up, and I'm going to have nothing here. It's going to be blank. Yep. And I have to go into settings, and I have to tell it some stuff. So this is where, man, if you don't have a base map to work with, you really have to know your stuff. You have to know what you have in the engine. And what I love about this is it really puts together your knowledge of engines and engine building and everything else. Now, today I'm wearing my EFI University shirt here. And as Ben Strader from EFI University said, he got into EFI tuning because he would build a good engine. He'd send it to a tune shop, and they would mess it all up, right? So then he got into the tuning side of it. So you would have to tell it how many liters the engine is. I want to say that Celica is a 1.8 liter engine, so that'd be 1800 cc. It's a 4-stroke engine, but you could see you could do 2 strokes, you could do rotary engines. How many cylinders? What do I want the max cranking RPM to be? You program in the VIN number. Our Celica is front wheel drive. It's a manual. And then, what do we think the minimum and maximum throttle demands are? We could program those in. And then I have to know the firing order, right? So it looks like it's defaulted to 1342, which I think that's what that Celica is. But if it was something else, I could change this around. It also asks us if this is an even firing engine or if it's an odd firing engine. If it's odd firing, I have to program that in, okay? But it's even firing, so I'd set that up. And then I go to the trigger and I got to tell it what type of crank sensor's on there and how many teeth are on the reluctor ring. So you can see that it gets a lot more involved on the initial setup if you don't have a base map to work off of. And that might be the case depending upon what type of vehicle you're putting this thing on. So let me check out. Let me check out the. Uh-oh, something's going on there. Let's see. Who's got their volume on? Jeremiah, I'm gonna mute you.
Jesus Christ, JJ.
Yeah. All right. Anyways, so you can see that like this gets pretty involved. If you're kind of an engine nerd like I am, I really dig this because it takes all your knowledge of engines and programming and puts it all together. And you know, it's not uncommon to see like a well-tuned engine might make, you know, 30, 40 horsepower or more than one that's poorly tuned, right? So it's pretty addictive to be able to change a couple buttons on your computer and all of a sudden you're making, you know, 10 more horsepower. It's a pretty cool feeling. Even just to wire in one of these computers, program all this information in, and have the thing fire up for the first time is really, really exciting. And as you guys can see, there's so much stuff that you can deal with. In fact, because I didn't have anything in here, it's got all the stuff for boost control, and so you can turn some of those features on or off. It's got a very generic fuel load, and notice that it goes positive in pressure because it doesn't know if it's turbocharged or not. So, and they give you a very generic base map here. So, anyways, lot of power here. You know, infinitely adjustable, and this is where you can really dial stuff in. And remember we talked about like coolant temperature. How does that come into play? Well, there's a whole coolant temperature correction factor, right? So you programmed in the base map. Okay, you programmed in the base map. Well, let's say the engine's cold. How's that going to affect it? Well, that's this.
How do you know what numbers to put in?
Good question. It's a little bit of like an educated guess, right? If you go, okay, well, I think this engine at wide open throttle, naturally aspirated, is going to be 85% efficient. You go to 85%, and then you look at the air fuel ratio sensor when it's running, and you go, well, was it running lean there or rich? Oh, it was running too lean. Okay, move it up to 88% and see what that does. And so for fuel, you're looking at response from the air fuel ratio sensor. You're looking at how much horsepower the engine's making.
So you would watch the fuel sensor while it's on the dyno,
exactly,
and then tune it to how it shows.
And when you're doing a wide open throttle run, like we were doing in class, where you take off and you go, right, and you run it through, what you would do is you would turn on your data log so that throughout the run, it records everything. So you could see, okay, at all these different speeds and loads, this was what the air fuel ratio sensor was seeing. Then you play that back,
so you
look at it, and then you make adjustments.
Do a dyno test before it.
Yeah, so you kind of do your best educated guess, and then you do a run, and you see what your air fuel ratio sensor was telling you on your data recording, because you're not going to be able to hold it at wide open throttle at 6,000 RPM steady to do that, right? You can steady state tune at like part throttle speeds and stuff, which that's where most people drive anyway. So that's the stuff you really got to get dialed in. But once you're getting beyond the like 50% throttle, you're going to burn up your dyno trying to hold those types of loads. So for there, you do a wide open throttle sweep test, you make a recording on your data log, then you go back through and play it back, and you see where the air fuel ratio was at different things, and you kind of make those changes, and then you do another wide open throttle test, and then you make more changes.
Or you could just drive a Volvo. That always breaks the dyno.
There you go. So I finally this week I finally got back in at American River College's campus. They finally let me in there, and it's just as we left it, broken dyno, the covers were off. I mean, it was just the weeds are all grown up everywhere. Exactly.
Were you able to put fuel stabilizer in the pit bike if you had a chance?
No, but I think I should be able to go back there next week and get that pit bike out of there. So Nathan, you and I need to get connected so I can get you back your bike. All right?
Well, I'm not doing much here anyway, so just bring it back. I believe what was there was my bike, my gas can, and my helmet.
Oh crap! Bike, gas can, and helmet. Where did we put the gas?
And my carburetor.
Okay. You will have to get connected because you get in there and you get kind of overwhelmed with all the stuff around and you forget. Like all the batteries in the cars were dead except for the ones that I had pulled in the shop and disconnected their batteries. And I was so focused on moving the stuff out for Sierra or getting stuff ready to move stuff over from Sierra College.
And if it is just a fuel ratio problem, I'm pretty sure I could figure it out here.
Yeah. So we'll get you your bike back. So hopefully this kind of makes sense. Like I said, you could download the software and mess around with it for free. It's pretty darn cool. I just wanted to show you how adjustable everything is, right? So just to give you an example, if I wanted to change the air-fuel ratio in a carburetor at wide open throttle, right? If I wanted, I would have to change a carburetor jet and it would kind of affect all these cells, right? Well, to do that, I'd have to drain the fuel out of the carburetor, take the top off, maybe change the jets, put it back together. To do that here, all I had to do was highlight those cells and type in the number, right? Or I could do my up arrow keys. Oops. I could, that's not up arrow, it's page up or page down. And then while the car was running on the dyno, I could be like watching it respond. So it's like more pain getting it all wired up and set up. But man, once you got it in there, the ability to make adjustments is pretty darn amazing. So I definitely dig it. So, all right, we need to wrap up today. So I will not save all these changes I did to that. What I will do is I will load up our Canvas web page, and I should just share that page. And I want to show you where these videos are. In fact, what I'm going to do is, where is it? Student view. I'm going to put it in student view.
That's a mess of screen I see. Wow.
Yeah.
This screen is a mess right now. It looks really bad.
So can you see the Canvas page now? With the pink stuff around the border, maybe?
No, not very well. Like
Really?
I see a pink border,
I can
but
see it just fine.
it looks really blurry.
Really?
Like looks weird.
I think that's Jonathan's internet.
I think that might be your
Looks
end,
fine to
John.
me.
Yeah, I think that might be your end. I'll tell you what on here, guys. I know everybody's got their video off because sometimes if everybody has their video on, we start running out of bandwidth. But
We were supposed to do like general knowledge quiz today, weren't we?
no, it's opened up today, so that's why I wanted to end today with this thing. Okay, so here we go. First of all, if you go to modules, some of the videos that I skipped over due for time, I've put those links on there. So like my question was, well, what's going to make a bigger difference on the dyno affecting the ignition timing or the fuel? There's a great video right here from Haltech on that. The dyno tuning one we were watching a little bit, how to wire in your EFI ECU system. So I have some great video links related to that. I have the complete EFI University classroom book on here for you as well. Last week we watched like how to degree your cam. I got all this, how to CC cylinder heads. So I have all these like links and resources for you in here under the modules tab. Now you mentioned that quiz. So if I go over here to quizzes, basically I have 2 tests, and this was kind of like, normally you would have done these tests in class anyway. So it's not like you're having to do more work. It's just, you know, in a different format because we're doing it on the computer. So I'm going to go in here, and so this thing just opened up today. It's not due till for a couple weeks when our class officially ends on May 18th, and you got tons of time, and you can do this test multiple times. Okay.
So how many more meetings are there?
What's that?
How many more Zoom meetings are there?
How many more Zoom meetings? Well, hang on to that question. We'll get to it.
All right.
Let me open up this quiz real quick and show it to you. This quiz, some questions are multiple choice, some are true, false, and then there is some short answer questions, right? Like, what items should be safety checked on the vehicle before performing a dyno test? The answer might be, make sure it's not a Volvo 5-cylinder front-wheel drive, or make sure Charlie's not driving. No, I'm just kidding. But anyways, different types of dynamometer.
Dyno killer. It's a dyno killer.
You know, by the way, the guy said that there was nothing wrong with the dyno. Like they said that amount of play was fine. They sent me 2 new sensors, and they said, look, you have to absolutely make sure the car is driven straight on the dyno. And then you just can't be getting all squirrely on their side to side. So you really have to be very delicate, because there has to be play in that dyno. That roller is so big that it has to have play, because it will actually heat up and expand and then shrink and contract. So they have to have play to compensate for the amount of expansion and contraction. So with that being said, that means that we just have to be really careful centering the car, and it can't be jumping off to the side, because that'll throw the dyno.
I think it was just a Volvo.
Well, really, it's like it drove to the side, and it jammed the dyno roller to one side, and it was tapping on that sensor, and I didn't realize
The Volvo is the dyno killer.
So if we have a car jump off the side of the dyno, our first step is going to be to pull the car off of the dyno, move the dyno roller back and forth, and then spin it by hand and make sure we don't hear that the sensor's rubbing it off. And then if everything feels good, then we can put the car back on there. So anyways, so these are the questions on this test, okay? And this is like, for me, this is the most important test for you guys, because it's your general tuning knowledge, okay? It's overall what we've been focusing on throughout the whole class. There's a little bit that we haven't talked about yet, because there's a couple questions on, trying to find the question. So some of these, remember, there's video links and stuff on Canvas to help you answer these questions. But there's a couple on forced induction, and that's what we're going into next week, okay? So there's that. I'm going to leave this thing.
So the forced induction ones, we can just Google the answers, right?
Well, I'll get that. So this is the calendar. So next week, we're going to start power adders, which is turbos, superchargers, and nitrous. So that'll be our last big lecture. And so by next week, the questions that you don't have the answer to, you'll have the answer to, okay? So that's this. So next week, that's what we're going to cover. And I'll get that presentation and stuff loaded on there and everything. Jonathan, your question was how many more weeks do we have? We basically have next week and the week after that. And
what about the people who have a little bit more knowledge in force induction, would they be able to just go
Oh yeah,
straight
you
into the
can
quiz?
remember it's unlimited attempts, so you can answer it. You can do everything. I just want you guys to know that there's like one or maybe two questions on that test that I haven't told you what the answers are yet, because we're going to do it next week, and that's on forced induction. Okay. So there's that. We have next week and the 15th, and the 15th is our last Zoom session. That would have been our last class period in a normal configuration anyways. So that's that's everything normal. I want to say the semester officially ends like the 20th. And so you want to try to get your stuff wrapped up, and so I can start putting your grades and stuff together. You guys that have been plugging along and doing your stuff, you're going to be just fine when it comes to your grades. Just make sure you do your test. Some of you guys need to go on there and comment on some of the videos. Like we just loaded on the one of 2.5 inch versus 3 inch exhaust, and you can see like Frank came on here, did some comments, and it's there's not necessarily like right or wrong. The idea is just to watch what's going on there.
I couldn't watch Engine Masters on Prime Video. It wasn't free.
No,
like
no, Engine Masters not. But this one episode is on YouTube. That's why.
Okay.
So this particular one, see the YouTube logo right here? This one is on YouTube, so that's why we're watching this one. So all the videos that I'm having you guys watch are videos that you can watch for free online, whether it's YouTube or the Power Block website. They're all ones that you can watch for free. Engine Masters, now you'd have to have a stupid Motor Trend on demand subscription to watch the other episodes, unfortunately. So some of you guys need to get on here and make some comments on the discussions. The other thing is there'll be one other quiz, which will open up next week. So it hasn't allowed me to open this thing yet, but I'm going to leave the student view so you guys can look at it. And this test is one of those ones where I just want you guys to try it. I'm not going to grade it as hard as the other one. This test here, this is from the guys at EFI University, and it's what they have their students do. So if you really like this EFI tuning stuff in the class, if that's really interesting to you and you thought, man, I might want to go to EFI University, remember as an ARC student, you can get a discount on their stuff. This shows you like the level of knowledge they want their people to have. So it's very detailed of what's going on in there. Now, how would you know all this information? Well, some of the stuff we have talked about in class, right? But there are some questions on here that are very very specific. Like, some of the stuff, like we answered this one today, acceleration enrichment, the throttle position sensor. Remember I said it acts like your accelerator pump. It lets you see how quickly the throttle's being opened. So that would be the right answer to that question. Okay, narrow band oxygen sensor. We actually answered that one again today. That's 0 to 1 volts. But so some of these ones, they're pretty mathy into stuff. How on earth would I answer this thing? Well, if I go to my course 325 and I go to the modules, and I go to resources here, you can see there is the tuner formula cheat sheet. So I have all the formulas for you here that would help you answer that question. on that test, or I also have the complete book from EFI University if you wanted to go through that. But remember, I'm not going to grade that test. It's more about the experience, so you guys can get a feel for like, well, that's if you were really going to be like a certified engine tuner, you know, there's a lot of stuff for you to know, and I just want you to have the experience of it. The test that unlocked today, that has the 14 questions on it, that's the one that's the real big priority for me. That's the one that has more weight to it. So you can see in the EFI University book, they have lots of formulas. Now these formulas are important because let's say you're making an EFI system. Well, you got to get the right size fuel injectors for what you're going to do with that engine, and so these formulas help you see that type of stuff. So anyways, to wrap things up today, don't forget that under the modules, there's a bunch of resources for you. And so you could, you know, if you want to know more about this stuff, there's definitely a ton of stuff you can do. So instead of watching meme videos or something, watch some of these ones. I think you'll really like this ignition versus fuel one. Yeah, watch this stuff. You'll learn a lot, and you'll have a good foundation. If later on you're going to build an engine or you're going to program a fuel injection system for it, you'll have a lot of resources for you to do that. And you can download a lot of these PDFs, save them with you, that type of thing. So we have next week, we're going to be talking about power adders, which is going to be a pretty big lecture because we're going to talk about turbochargers, superchargers, and nitrous. And then the following week, we're going to just kind of wrap everything together, and we'll talk about breaking in a new engine, and then just, you know, what's going to happen in the fall and stuff. Okay. So any questions on the stuff from today? And let me punch up the chat, see if there's anything there. Well, if you guys don't have any more questions, sorry we went a little bit longer than I intended, but I wanted to share all those resources for you. Is there a final test in the class? Yeah, so that 15 question test, essentially that and the EFI one, those will constitute your final. The 14 question test is I'm assigning more points to it, so that essentially is like your final. And then the EFI University one adds some stuff to it. But that's it. It's just those two tests. Go on there, participate in the discussions. I'll probably make a discussion about the video that's the ignition versus fuel. But that's it. So we'll put everything together from that. Now, after all this stuff, I don't know about you, but I'm chopping at the bit to get on the dyno and everything. And we'll be doing that in the fall in the skill and speed development class that I'll be running on Fridays. And so that'll be kind of like open lab for you. So if you want to work on your Volvo and change the throttle body for the 10th time, you can do that, or put new spark plugs or brake pads in something, or if you want to run something on the dyno, you can do that as well, because we'll have that stuff open. So good question. Is there any other questions? All right, guys. Well, what I will do is I will stop my screen share so we can see you guys. You guys, all have a great week. Hopefully everybody's staying safe out there. I am seeing a lot more people out and about as the warmer weather comes in. So hopefully you're not going stir crazy too much. The French garage is slowly coming along. You notice I got a big 4x4 there helping me hold up my rafters because I got all a bunch of stuff up there. And hopefully by next week I'll have my race car in the garage here. So you guys all take care. I hope you're getting to work on some stuff and have fun. And you're
I
probably
just changed out a gas tank on my quad actually, and I
nice.
Running again.
Nice. And I bet you're all becoming pretty darn good sim racers, aren't you?
Yes, I've been doing a lot more on like mobile device racing.
Okay, well, if you
I've
guys
also
are
been
ready,
watching the Pro Invitational series with Jeff Gordon racing again finally.
Oh,
Yeah,
is that on the iRacing NASCAR? Was Jeff Gordon racing on
Jeff
that?
Gordon was racing.
How did he do?
He did really well. It was like
I
watching
watched
him.
some of them. I didn't watch that one though. Okay,
Yeah,
so
it was like watching him back then in like 2004.
you can't. Oh yeah, you can kind of. So I'm setting up my sim back here. It's almost there. It's not quite, but pretty soon I'm going to be jumping on the iRacing bandwagon as well. So, um, anyways, so yeah, if you find that you're really enjoying the simulators, the sims that I recommend, but they're all computer based, but they're pretty good. Is Assetto Corsa. What I like about it is it's open architecture, so it's kind of like I'm sure some of you guys are younger, so you've played like Minecraft where there's mods and stuff. With Assetto Corsa, people can make and design their own tracks. So I like that one. And then of course, iRacing's the big one. Like if you want to do online racing against other people and really have it very standardized with leagues and everything and have a pretty realistic physics package, iRacing, although it's expensive, it is pretty hard to beat. And I will say that you can get like an initial subscription. I want to say they have like a 40% off, so you could sign up for like 1 month or something and try it out. Yeah, it's cool to race against other people.
I gotta say, I think if I did get an iRacing subscription, I would mainly be doing Lucas Oil trophy truck racing.
There you go. Well, and those are pretty. It's amazing how much different, like the different vehicles do drive quite a bit differently on there. I've done that a little bit, and yeah, it's pretty cool. It's yeah. So and we have been doing the Fanatec versus the Logitech. There's some things I like better about our little Logitech. I really like the shifter on the Logitech, but the Fanatec does have it's less jittery. There's less like gear backlash in there. But I'm still trying to get the Fanatec to work right. So anyways, you guys have a great week. Next week, remember, power adders, superchargers, turbos, and nitrous. And I got some fun stories related to that as well. Everybody stay safe out there, and we'll catch you next week, okay?
All right, see you guys next week.
All right, bye for now.